Video is going to discuss my solution to the Chapter 5 case. So we're considering some new supplier, and the supplier is supposed to give us some part that's 8.5 centimeters, in diameter, whatever the measurement is. And we have some tolerance specifications that say that it can be between 8.4 and 8.6, but not outside of that. So anything outside of 8.4 to 8.6 is deemed unacceptable. Anything between 8.4 and 8.6 is okay. So we want to check out the supplier. We get 99 parts, as you can see here in the data set, and we want to use these to evaluate whether the supplier is any good. Now, if you read the case, it says that at the price that we're being charged, we could live with 10 or even 20% defects. Sounds kind of high to me, but we'll just go with that. All right, so the question is, what percentage of these parts are defective? So let's go up to Analyze, and we're going to use Explore, and we'll copy X into the dependent variable list. Actually, I'll reset things. I was checking things. So let's bring X into the dependent variable list. The other thing that I want to do is go into plots for a second. And by default, SPSS gives me a stem and leaf diagram. I don't want one of those. Let's get a histogram instead. Go hit Continue and go hit OK. Now, the case leads you down the wrong path. So let's go look at our means for a second. And what you'll see is the mean is pretty close to what it's supposed to be, 8.5. We go to the standard deviation, it's about 0.1. So recall that we want to be between 8.4 and 8.6. Now, if you go one standard deviation from the mean in either direction, you're at about 8.4. If you go one standard deviation of 0.1 less than that, and one standard deviation to the right of that, you're about you're at 8.6. Now, the case is leading us down the wrong path when they remind us of the empirical rule. So remember what the empirical rule says. The empirical rule says if you have a normal distribution, then 68% of the data fall within one standard deviation of the mean. Well, clearly in this case, if the data is normal, then 68% of the parts would be acceptable, and that means 1/3 would be unacceptable, and that defect rate would be too high. Okay, but that empirical rule depends on one important condition, and that is that the data are normal. So let's go look at our histogram, and what you'll see is the data are nowhere near normal. Okay, so you've got a very big spike, and then you've got some extreme outliers. So the story is that this supplier is really good much of the time, but when they're bad, they're really bad. If we go look at our box plot, the story is the same. So almost all of the data is in a tiny wedge here. That's your box plot, but then you've got some horrible outliers. So in essence, the data are not normal, so that empirical rule doesn't work. If you look at the value of kurtosis, remember kurtosis must be 0 for a normal distribution. Well, 27 is way far away from 0. So that means you've got very thin tails. Skewness is also not 0. So we don't have a normal distribution. Just forget the empirical rule. Siegel has led you down the wrong path. Now, question is, what percentage of these are non-defective? Well, the best way to do that would be to come over to the data set, and I'm going to show you a couple ways. Let's just do a simple point estimate of this. So what fraction of the cases are between 8.4 and 8.6? I'm going to show you two ways to do this just to kind of build up your SPSS skills. Let's go up into data, and I'm going to sort. So data sort cases, bring this in, and hit OK. And so a very crude way to get at this would be let's count those between 8.4 and 8.6. So it looks like there's 5 cases on the lower end that are bad. If we go to the upper end, 5, okay, we have 6, 7, 8. So 8 cases out of 99 are bad. 8 cases out of 99. So let's just bring up our little calculator here. 8 over 99 equals, I would estimate a defect rate of about 8%. So remember, the case said we could live with 10% or even 20% defects, so therefore we ought to be using the supplier. Let me show you one more way to do this. What I did by counting the outlier, the bad values, defective parts, works great when you have a little data set with 99 cases, but if I had tens of thousands of cases, this wouldn't be so practical. So another way is I could define a variable. Let's go up to Transform, Compute. Let me reset this. And I'm going to define a new variable, OK. And so OK is when x is less than 8.6 and x is greater than 8.4. So this is a Boolean expression. Boolean expressions evaluate to 1 whenever they're true. So whenever both of these conditions are satisfied, it's going to be true. It's going to be 0 otherwise. So go ahead, OK. If we go back to our data set, what you will now see is this new variable OK in the data set, and it does what I did by hand. So with gazillions of cases, this the second approach is going to be better. Now I need to find what percentage of the variable OK equals 1. So there's a couple ways we could do that. Let's just do a frequency distribution. So we'll go up to Analyze Descriptors Frequency. Let's bring OK in and go hit OK. And here we go. We get exactly the same answer as with my pocket calculator. 92% of the cases are OK. 8.1% are not OK or defective. Okay, so in summary, you can't use the empirical rule unless you have normal data. We don't have normal data as revealed by the box plot, the histogram, skewness, and kurtosis. What's the best way to estimate it then? Well, let's just count the percentage of OK cases, and we did that in 2 different ways. So we love this supplier, only 8% defects when we can live with 20. We should go with it.